definition, the integral of f of z times the absolute value dz, what does that mean? Well, what that means is, so I say two things. I say one, on the one hand, you could define it as the limit as n goes to infinity of the sum, and I'm using the same nomenclature I did at the start of class, so it's that same, jibber jabber. F of zj modulus of zj minus zj minus 1. But if we go through calculations similar we did to the start of class, you could prove that that's in fact the same as looking at the integral from a to b of f of gamma of t times the modulus of d gamma tt, the length of the complex derivative, dt. Right. So as a particular application of this, you could talk about the length of a curve as being the integral over gamma of that. So of course that would just be the integral from a to b of the square root of dx dt squared plus dy dt squared. Like that's what this works out to, which of course you should recognize as being the arc length integral. All right. Now we have a theorem. This is the so-called ML theorem. And the ML theorem, it states the following. Well, this is part one is not the ML theorem. Number one is not the ML theorem. So this is part two is the ML theorem. Number one simply states that the modulus of the integral of h of z dz is less than or equal to the integral of the modulus of the h of z integrated over the modulus. Now we need to come up with a name for this thing. So this is the arc length integral is what it is. Really, the modulus of dz is the square root of dx squared plus dy squared. I mean, it is what we usually call ds in like Calc 3, truth be told. That's what that is. So first of all, this is one result you have, that the modulus of an integral is less than or equal to the arc length integral of the modulus of the complex function. And the thing which is surprisingly useful is what follows next, too. If you have that the modulus of h of z is bounded above by m for all, z in this notation here, guys. This is the notation I've called that the trace before today. I called it gamma of AB. It's the set of points that are on the path, all right? It's the actual point set that gamma is parametrizing. Then the integral over gamma h of z dz, modulus of that, is less than or equal to m times L, where L is the length of gamma. All right. And I am going to use the projector to show you the proof of that because I don't feel like writing it at the moment. And the proof is like very, very easy if we use the Riemann form. It's quite subtle if you take the parameterization definition as your basic starting point for the complex integral. Like the proof of the ML theorem is much more nuanced if you take the parametric as the definition. But if we do take the Riemann as the definition, which we can, it's relatively harmless, the proof here. All right. Oh, come on. All right, so here at B. So the proof, I mean, by the way, number 2 follows from number 1 pretty obviously, right? Like, if we know number 1, we get number 2. That's hopefully clear. So we're taking the modulus of this finite sum. The triangle inequality says that that's less than or equal to the sum of the moduli being added. Like the sum of, so if we're adding together a bunch of things, then the triangle inequality implies this directly. But then the modulus of a product is the product of the moduli. And as such, like you proved this or didn't prove this on test 1, you may recall. But once you know that, we, that was supposed to, I don't know what happened there, that's weird. But so that's the one thing. And if you pass to the limit, that's number 1, because the integrals, the finite sums become integrals in the limit, the Riemann sums. And likewise, if we have a bound, if this is less than m, we get m times that. And again, if we take the limit as n goes to infinity, this gives us the arc length, whereas that gives us the integral that we're bounding. So that's the ML theorem. The alternate proof, if you wanted to prove it from the perspective of the, taking the parametric integral as basic, the ultimate proof, you need this lemma, and then you do this calculation, and after some hocus pocus, you prove it. It's not that easy, and I'd have to spend 10 minutes explaining that. But it's like 2 minutes for if we take the Riemann sum, like I just did. So, what good does that do us? Well, let's see here. So I have integral of 1 over z on the unit circle. If we take the modulus of z, we get 1, right? So 1 is a m for 1 over z. And so the ML estimate shows that the integral of dz over z is less than or equal to 2 pi, because 1 times the length of the unit circle is 2 pi. That's pretty good, right? We calculated it was 2 pi I. So what's the modulus of 2 pi I? 2 pi, right? It works, yay. Here's a less stupid example. If we were trying to integrate dz over z squared plus 6, how do you bound 1 over z squared plus 6? Well, there's a handy-dandy triangle inequality. So this is larger than that, which makes this fraction larger, because I was saying this is larger. So we made the denominator smaller, which makes the fraction larger. But this is also equal to the modulus of z squared, which would just be equal to r if we're on the circle of radius r. And so this gives us a bound on that, provided that we're on a circle that's like larger than, I think, radius squared of 6. So we get this estimate here. The integral of dz over z squared plus 6 is less than or equal to pi r, because that's the 2, why do I have pi r, not 2 pi r? Oh, I'm doing half circle. So the half circle. Oh yeah, we're doing the half circle because this estimate is available to us on the half circle part, right? What happens on the integral from minus r to r is a separate story. But the half circle part is bounded by this, right? the circle part of the half circle. The diameter part, separate story. But notice what happens as r goes to infinity here. Well, if r goes to infinity, that goes to 0, right? So this will allow us, this kind of argument will allow us to say that the integral of a complex function over like a half circle, right? It's just going to be equal to the integral along the diameter if we let that half circle become very, very large, because the piece that comes from integrating the circle part of it goes to 0 by the ML theorem. This is a typical calculation that we do later on. All right, so that's the ML theorem. And that brings us to the last thing I wanted to cover for today, which was this, because I wanted to explain to you why all these integrals are 0. All right? So we say f of z is a primitive of big F is a primitive of little f on D if the complex derivative of big F is little f. You can call it antiderivative. We will call it antiderivative. It's called primitive here simply because I was making these notes based on Gamelin's complex analysis where he uses the word primitive, and it's kind of a hangover from function theory. But we will call it antiderivative. That's fine. I just want you to know primitive is another name that's often used for it. But it is antiderivative. It's the antiderivative, right? Obviously, it's not unique, right? But if there is a primitive for your integrand, and if this curve goes from A to B, just that. So the reason I knew that your integral of Cauchy around the circle was 0 is because I know that the antiderivative of Cauchy is just sinh. And so I know if I integrate around a circle, I can just take the beginning and ending point to be the same point. So sinh of 0 minus sinh of 0, or sinh of point minus sinh of point is 0. So I knew the integral of Cauchy was 0 when you brought it up. But I also knew I did not want to calculate that from the definition because it would give me 1/2 e to the I, e to the it minus, no. Why what? Lowercase? Oh, I don't know. That's a good question. I think lowercase a equals capital A here is the quick answer. The larger answer is I have no editor. But so also that's why I knew this was 0 in my example. Oh man, I didn't number this example. What was it, example 5? Yes. So back here in example 5, see, I knew that that integral had to work out to 0 because I know that, d dz of, z cubed over 3 is equal to z squared. So if this is f of z, this is big F of z, right? And so if I want, I can, take my half circle and I can take this point R is equal to big A is equal to big B. And so if I'm integrating, over that curve, I know it's just, z cubed over 3 evaluated from R to R, which is just stupid. 0.
So is this like conservative vector fields?
It's similar to conservative vector fields, I suppose. Yeah. So the last thing I'll do for today is just prove this theorem for you guys. But I should write that out, I think. So how do you think we're going to prove it? Oh, man.
Probably using the definition of the Riemann integral.
How about not? Let's not do that. I mean, yeah, that does seem like the logical answer given everything else I've done today. It's like it's got to be the Riemann integral. No, I'm gonna zig instead of zag. Let's see here. So we're gonna assume what? That you have f equals to u plus iv with big F such that df dz is equal to little f, right? And we're going to let gamma, and we're just going to do it for we'll say gamma of A is P and gamma of B is Q. So let's integrate over gamma of f of FTZ, right? So that's the integral of u dx minus v dy over gamma plus I times the integral. Oh man, just a second. Let me not make this overly complicated. I have this sense that I'm doing it the wrong way. Ah, yes, I'm doing it the wrong way. So, my bad. So, let us put it in. This is big dFdz, right? But yet another way you could look at the formulas I gave you today is that this is really the integral of dFdz dx plus I times the integral of dFdz dy, right? Which I could write out, but let's use the Cauchy-Riemann equations, right? The Cauchy-Riemann equations got to come into play here. So remember dFdz is what? Partial f, partial x, that's part of the Cauchy-Riemann equation, right? That's how we calculate the complex derivative. It is partial derivative with respect to x, right? And how does the y derivative go? If I want to write that as a y derivative, what do? I think it was minus I partial f partial y, is that right? If in doubt, work it out. Let's see here. So we have big ux equals to big vy, and big uy equal to minus big vx. I'm supposing that big F is big U plus I big V for the sake of discussion here, right? So we know that big df dz, at least we remember this much, right? It was ux plus I vx, right? But if we put in the Cauchy-Riemann equations, that is Vy minus I times Uy, right? Which is minus I times Uy plus I times Vy, I believe. So yes, indeed, you have df dz on the one hand is partial f partial x, but we can also write it as minus I partial f partial y. That's just a review of the Cauchy-Riemann business. So what do we have? So I say we have, partial f partial x dx plus partial f partial y dy. And what does that technically mean? Let's write out the details here. So we're talking about the integral from a to b of partial f partial x dx dt, right? Plus partial f partial y dy dt dt. By the definition of the integrals. But what is that by the chain rule? What is that?
Yeah.
You say what?
DF.
Oh, df dt? Yeah, essentially. I'll write it out a little bit more explicitly, but it's ddt of f of gamma of t, right? I mean, fair enough. I don't have the... in my current notation, I guess it's f of x of t, comma, x of t plus I y of t, if you like. But that's an expanded notation for gamma of t in this discussion, right? The point is that this is that chain rule that we worked out for the composition of a complex function with a complex path. We use the Cauchy-Riemann equations to prove that the regular chain rules of calculus 3 are tantamount to saying that it's, you know, it's this. Well, anyway, this is a chain rule. And so then what? Well, you just got f of gamma of b minus f of gamma of a, because you've got the integral of a total derivative. But that's f of, I guess I called it q, minus f of p. And this is the fundamental theorem of calculus for the complex integral. It is well, we need there to be a primitive that's defined on the whole curve. So let's think back to our interesting example today, like why didn't it work? I was trying to integrate. We'll just stick with dz over z for the moment, right? What is the antiderivative of 1 over z? Natural. Well, but this is complex, so not natural log, but what? Log, right? So we could do logs of alpha of z, right? Plus a constant. I mean, so there's also this notion of indefinite complex integral. So we want to kind of mimic our notation from before. So if there's, I guess I shouldn't put a c here, but if I just talk about the indefinite complex integral, we could use that as a notation for the antiderivative. Of course, if I try to do this for a loop, for a circle, what's the problem? You know, if I've got if I've got a circle, I mean, we'll think about it, right? We can think about two circles, and then we'll end class for today. So if I have a circle like this, say C1, if I have a circle like this, say C2, what's the difference if I integrate? If I integrate, say, dz over z for C2, what can I do? Yeah, make a choice for me. Which log should I use? Regular old log, right? So we could use, log of z evaluated from, let's call that point P, from P to P, which of course is 0. And that would be a legit calculation because the branch cut for this guy, it's over here, right? And it's not going to affect you over there. You have a continuous log all the way around. It is serving as an antiderivative on the totality of the circle, so that integral is 0. But once we encircle the origin, it doesn't matter what choice of alpha you make. It's somewhere. It's here somewhere, right? And no matter what alpha you pick, we can't actually do this integral with the fundamental theorem of calculus for line integrals, right? It's not quite right because, if I make this point P, I can't just do, that's not allowed because it is not an antiderivative on the whole circle. Yeah, the discontinuity is giving you that 2 pi I.
But then there's 2 on, if you were to pick a ray that goes through C2. So, well, not necessarily.
There is no discontinuity on the C2 is the thing.
Well, if you were to pick an alpha, so that there is.
Oh. Right. Good point. It would cut, if we were to, that's an interesting, I like that question. I'll remember that question. That's a good question. Yeah, why? if it's on the next test, it's Shane's fault. Yeah, probably it's true. I'll name it Shane's problem. But you've got a good point. If we were to foolishly mess it up and pick a wrong log that went through there, we'd still get the right answer probably, in as much as we ignore the fact that it's illogical. You know what I mean? Like, we could do a wrong calculation. We could still calculate, like up here, you know, and get 0 and ignore the fact that it's not really a well-defined calculation. It's kind of like sometimes people do stuff like integral of dx over 2 square root of x from 0 to 1. Oh, square root of x. Value from 0 to 1. Square root of 1 minus square root of 0. That's 1, right? Well, it looks nice, but there's a little problem. That's an improper integral. So you should be thinking about a limit at least. And if we take the limit as t approaches 0 from the right of the square root of t integrated, you know, it actually gives the same answer. But if we don't understand that, then, you know, there's something missing. Yeah, well, the derivative of the square root is 1 over twice the square root. Right? Yeah. What'd I do?
No, why is that wrong?
Because this original integral has division by 0.
Oh, right.
So it just happens to be right. That's a happy accident. Just like it's a happy accident that if we did pick a log that branch cut through the circle twice, and we ignored the fact that it wasn't a proper application of FTC, we'd still get the right answer of 0. But we would be technically incorrect in the same sense that this is technically incorrect, you know?
But you can also do the limits, and that's
That's true. So if we wanted to repair this, what would we do? We could do something like this, right? We could say, well, it's really the integral. Let's call, let's pick this as a starting point, right? So this point right here, we'll call that C alpha from below. I'll call it C alpha minus dz over z, plus the integral over, you know, C alpha plus dz over z, where I more specifically mean a limit, like a limit. I don't know, I have to write out a bunch of stuff, but we could set up an integral that goes from here to here and take the limit as you approach the ray from that side and do that piece, and then take the integral from all the way around here and take the limit as you approach the other side. And if you did that, you could calculate the integral with the log and get 2 pi I.
And if I can ask one more annoying question.
Go for it.
What if the ray is tangent?
If the,
Goes there once.
you mean the,
The ray of discontinuity.
So you're thinking of, we should have football games all the time. This is great. This is the best.
Except that when I went to take my test for 497, I found out that the testing center closes at noon.
If only someone had forecast this difficulty. If only someone had forecast this very happening. If someone had done that, that sure would have been handy. Oh, that's right, I did that. Because I know a little bit about the testing center and their glee at not working. So given an opportunity, they will.
Because we were supposed to have it today, but we're not supposed to have class today.
Well, what if everybody was busy before noon and couldn't take their test?
Well, we have it tomorrow.
Yeah. So you're, So you're saying, like, suppose something like this, right?
Precisely.
And you're talking about integrating 1 over z?
Yes.
Yeah. I'm pretty sure that the answer's, I mean, I know the answer is 0 because that branch has nothing to do with it, you know? Let's see here. So I think I could do something like this. Integrate from t to 2 pi minus t, the limit as t goes to 0 from the right. So what I'm doing is I'm imagining like this, you know, and as t goes to 0 from the right, it's squeezing down to give you the whole circle in the limit. Like that. And I don't have a notation. I need a notation. Let me call this thing c sub t, right? So technically I should put like c sub t here. What do we want to make this? Like minus 2 plus I, maybe? I don't know. So, you know, z is equal to what? Like minus 2 plus I e to the, yeah. I'm trying to think of a formula for it. I guess I just do e to the t minus pi over 2, maybe. Because then that will, when I put t equal to 0, I'm there. So, and then I think if I do I should use theta here, sorry. And then, so for like t less than or equal to theta less than or equal to 2 pi minus t, I think that would be my c sub t. So that starts at e to the t minus pi over 2 times I, so I think that's like right here. And then it goes to nearly 3 pi I over 2, which relative to here is like that. I think this is the right parameterization for it, but you know, I'd fuss over that. So that's my c sub t. The point is, at no point does c sub t cross the branch, right? So that I can legitimately apply the FTC2 to that curve, right? So so I can say, well, that's the limit as t goes to 0 from the right of we were using log to try to make our life difficult, right? So what do I have? I've got what, minus 2 plus I plus e to the what minus I times t minus pi over 2. Oh wait, I'm sorry. No, this one first, right? So e to the 2 pi 2 pi minus t minus pi over 2 minus the log of minus 2 plus I plus e to the I times, what was it? T minus pi over 2. I mean, this should work out to 0. But this is a very silly way to do the calculation, but you know.
Why would that not work for C1 as well? Why can't you use that for the same argument to get C1 and 0, or the interval?
Well, I think for, basically the issue is that for t close to 0 but not equal to 0, if I was to zoom in on that point right there, right? The issue is that both of these points, when I feed them to the log, right, they're both still in the same case for the logarithm. So that's why that ends up being 0 when you sort through it. In contrast, when the picture is like, you know, like this, and your, you know, limiting path is going, you know, like the one side's here and the other side's there, well, they're in different cases of the log, and so that's why the difference gives you that 2 pi I.
That makes sense.
Yeah, yeah. So, so this here, of course, these both, anyway, I'd be here 10 minutes calculating that.
Yeah, I'll have a little bit of faith with that.
Okay, good. But anyway, yeah. So next time we will look at, you know, more on how we can use the fundamental theorem of calculus, and we'll also look at what's called Cauchy's theorem, the first of many of Cauchy's theorems. This is the Cauchy's theorem that is like an immediate corollary of Green's theorem in like Calc 3, which you guys remember because you have a complete and working knowledge of Calc 3 that you've kept with you since you loved Calc 3 very deeply, and it means so much to you that you've remembered all of it, right?
Oh, totally.
Okay, very good.